And when G is greater than or equal to 2, then X is, well, it is canonically polarized. It is a curve of genus at least 2. Okay, so that's kind of purely algebraic. There was nothing particular about complex numbers going on here. But from now on, I will actually try now to actually view these as complex manifolds. So I do care about that I have the ground field, which is C. Projective complex manifolds. So this is, so this is just if I want to, I'm not going to be that pedantic in a little while, but in principle, so when I'm given, if I have extrinsically, say, smooth, so complex, projective variety, so just something algebraically, X sitting inside Pn, right, over C. So then you get a complex manifold, by which I really mean, I'm not going to give the definition of a complex manifold, but it's a topological space with a pretty good topology, so locally it looks like a ball in Cn, and then transition functions are holomorphic and so on, which is something that in principle you don't have here. This would be the Zariski topology or something. So this, if I'm pedantic, this would be like an XH, where H is for holomorphic. There's some kind of analytification of X, right? And of course, it's just done by you, just locally, given by these solutions to the polynomial equations, and just by the implicit function theorem, you know that you're gonna that defines a complex manifold. Right. On the other hand, as long as I'm projective, so projective would just mean that it sits inside Pn, right? So X, so this guy sits inside kind of complex projective space, which, again, if I stick with being a bit pedantic, this is also a complex manifold, simple one. And in fact, of course, you have Chow's, well, a version of Chow's theorem. So any complex submanifold of say Pn, if you want it like this, is algebraic. So it's projective, so it's really given by algebraic equation. Okay. All right, fair enough. So now, but now once you have a complex manifold, or view such a thing as a complex manifold, then you have additional structure. So I want to spend some time talking about that. Because I need it. I may not use exactly the same notation and terminology as other speakers, so nothing else, I want to do that. So this is an additional structure on Kx, Kxh. So now I'm just going to write this. This becomes kind of unwieldy, so from now on I'm actually going to identify just the complex manifold with the kind of the algebraic variety itself. I don't think there will be a lot of confusion. So first of all, you can talk about Hermitian metrics, in particular Kähler metrics. So I'll be a little bit sloppy here. So what I mean by Kähler metric, I really mean the Kähler form. So this is going to be, say, a smooth, positive, closed 1-1 form on X. Right. And if you started with something, I mean, if you are in this, if you are a projective variety, these always exist, but there could be many of them, so you might have some choice. And in particular, if you have a polarized variety, so you may want to require that actually this omega lies in the first Chern class of L. Okay, so maybe times some suitable constant, but let me not worry about that. Okay. So once you have a Kähler metric, I mean really a Kähler form, that should be maybe, so this induces a Hermitian metric on X. I mean just a Hermitian inner product on each tangent space, and then varying in some smooth way. And then if I just very roughly forget a lot of things here, then this induces, I get a metric space from this. So from metric is used in different ways. Here I just mean like a distance function on X. Okay, so that's one thing. Now once you have line bundles, you can also talk about metrics. As I said, it's kind of an overloaded word. You can talk about metrics on line bundles. Here I think of a line bundle not just as a kind of invertible sheaf, but actually I want to think of it as a total space. So I can have L and then a map to X. So here is a bunch of lines essentially. Maybe they kind of curve a little bit, but anyway. And you have the zero section. So this is X, and then above X I have an LX, which is essentially C, except that I don't have a particular, I don't know what 1 is here. Right? So, well, first of all, I'm going to use additive terminology for on both line bundles and metrics. I'm not sure if I'm really going to use this formalism that much, but just in case I do, let me mention this now. So I mean, so what is a metric is a way of measuring just lengths inside Lx, or if you want just to define what the unit disk is inside each Lx. But here, right, so instead of, so what would be, so this is kind of usual maybe how you do a metric, so this is kind of something that's, right, so a metric would be something that just measures how, where you are and how far out you are from the zero section, and it takes just the norm. So instead of using that, I'm just going to use, say, phi to be minus the log of this thing. So this goes from L to, in principle, to, I guess, R union plus infinity. Or if you want, maybe L minus the zero section to R. I mean, of course, this is just maybe a natural log or something. It doesn't do very much. But with this terminology, you can get, I mean, it becomes, for certain things, it becomes more natural, well, easy to write down. It's, of course, equivalent. So if you have, for instance, if you have L1, L2, these are line bundles on X. And if I have P1, P2, say these are metrics on L1, L2. And if I have, say, I don't know, R1, R2, and Z, then I can say that I can do R1, P1 plus R2, P2 as a metric on R1, L1 plus R2, L2. Okay. There's one thing. Just functions on X. So I'll just evaluate at just a section 1. Right. Okay. So I should say, I mean, so this is maybe not completely standard, but it's very useful. These kind of functions. I know, just a line bundle is essentially, I mean, the section of a line bundle is almost like a function on the underlying variety. In the same way, a metric is essentially the same thing as a function. So functions, these phi, I mean, sometimes these are sometimes called weights. I mean, the weights of the metric. Okay. Now we have curvature of metrics. So I mean, you have the Kähler metrics and metrics on various line bundles, and of course there's some connections between them. So if I have, suppose in this terminology I have phi is equal to some, well, so far I only looked at smooth metrics, but on L. So if I have such a thing, I'm going to define, with a slight abuse of notation, I'm going to define DDC of phi to be equal to, well, minus I over pi. So this also defines some version of DC here, but I'm not going to worry too much about the normalizations, but this is what I want. And then I do D bar, and then what I do is I take log, and I evaluate any section like this. So this is, so S is some local non-vanishing, nowhere vanishing section. Right. So this doesn't depend on the choice of section, because if any other section would be just the same as S times F, where F is holomorphic, and then you get an extra term which is killed by DD bar. Okay. So it's convenient terminology, but I should maybe say, just note here that with this terminology, DDCP is not exact in general. Right. In fact, this DDC phi actually belongs to, it's a positive one, it's a 1-1 form, which is in the Chern class of L. So, okay. And you say that phi is positive if, well, this DDC phi is strictly positive like this. So it just means that the same thing as, well, DDC phi then is a Kähler form. Sorry? Yeah, sorry, yes, holomorphic section, yes. Yes. Okay. Then we have one more thing. So this is kind of metrics on various line models. But this canonical bundle is especially important, and metrics on canonical bundles, metrics on the canonical bundle have kind of a special role. All right, so let me write this somewhere else. So if I have, so it turns out that the metric, so this will be, is kind of implicitly used a lot. And this is the fact that there is a one-to-one correspondence between metrics in the sense on the canonical bundle and volume forms on X as say like a Riemannian manifold, right? So there is a, so if I have metrics on Kx, so this is a one-to-one correspondence between, say, volume forms, by which I mean kind of there's a smooth positive measures on X, right? So this is essentially standard, but let me, so in my terminology, I want to define this as kind of e to the 2 psi. Okay, so if I have a metric on Kx, so I mean, what is this thing? So this is defined to be, what I do is whenever I have, sections of Kx, holomorphic sections are holomorphic n forms. So I take such a guy, and then I divide it by the norm of psi squared, right? So here is, right, so here is, if eta is a holomorphic n form, so, and this eta squared is like essentially just eta, which eta bar, except that I might want to normalize it to really get a form. So like maybe I to the n squared, and well, depending on your taste, you want to divide by 2 to the n or not. Anyway, and then you normalize by this number, and then it doesn't depend on eta, so it's kind of a local. All right. And then in the other direction, just notation-wise, I'm going to say that if I have a dV here, so a kind of volume form, I'm just going to write this. I mean, with this notation, this is like 1/2 log dV or something. All right. So that's quite useful. And then it leads to Ricci curvature, which I'll present in a slightly different way than in the previous talk, but it's equivalent, but it's very much adapted to this kind of specialized situation. Of course, Ricci curvature comes more generally in Riemannian geometry. So it's kind of a tailor-made definition. So So if I have omega, which is a Kähler form, on x, so of course I can take omega to the n, and I might want to normalize, divide this by n factorial or whatever. But let me just do it like this. So this is this is one of these volume forms. The smooth positive measure. So I can take, well, if I take 1/2 log in this terminology, omega to the n, then this is a metric on kx. And then if I do a negative sign with this is a metric on minus kx, right? So then I get, and I define the Ricci curvature. Again, it's not so much, it's really as a definition, but of course it ties in with more general situations, at least up to normalization. So this would be ddc of then maybe minus 1/2 log omega to the n. Okay, so this is something that lies in C1x, which is C1 of minus kx. Okay? So given a Kähler form, in some cohomology class, you get a new form in closed form in this C1 of x. Right. So as Binge already talked about, you have so let me not say more about the history here, because it was already done. Right. So this is, it's not just Yau, but I guess after all, Yau is maybe if I have to name one person, I'll do that. So for if I fix any Kähler form, so let me call this omega 0 on x, then the map taking, so the map from Kähler forms, so taking omega cohomologous to omega 0 to, I guess, closed 1-1 forms in C1 of x. So this is the map that takes omega to Ricci omega. So this is, the main point is surjective, but it's bijective. Okay. So now, again, I'll continue, so it'll be very close to the last talk, but I think that's okay. So I'll say something about Kähler-Einstein metrics, and then I'll finish by talking about generations a little bit. Then we'll. All right. So Kähler-Einstein metrics are they're kind of where the Kähler form is related to the Ricci form. They're proportional. Right. So you say that the same. So a Kähler metric omega on x is so let me just say Kähler-Einstein metric. If its Ricci omega is proportional to omega. Right. And again, as was observed, so after scaling, if I multiply omega by positive constant, the Ricci doesn't change. So I can assume that lambda is either 0 or plus minus 1, right? And then you have the three cases. So I'm just going to repeat essentially what was said before. But anyway, so this is the main case for us. So this is when the Ricci is 0. So this is kind of the Ricci flat metric. So of course this is only possible if this implies that C1 of x is 0, which I guess is a weaker condition than what I call Calabi-Yau. Well, let's ignore that, but it's essentially the same. In any case, Yau's theorem implies that any Kähler class contains a unique Ricci flat represented. So for every omega 0 Kähler, there exists a unique omega cohomologous to omega 0 such that this is 0. Okay. All right, so let me briefly mention the other two cases. Such that, in any case, so you can look for this, right?